There he is.
There's the myth. Okay, so let's have a quick look. We'll just go through. How about some of these problems on the assignment? And if you haven't read the chapter, read the chapter. Consider that an assignment.
PR2.
What am I doing? PR2? Oh, yeah, that's right. We already did PR1. PR2, there we go. PR2. Okay. All right, so something like this. Okay, let's make this a little bigger. How about? Okay, 100% efficient. So, real quick, and let's take a second and just review, because I'm not sure everybody remembers exactly. Don't look up here. See if you can just, without looking, see if you can kind of reason through this, because I want it to make intuitive sense. What is efficiency before we even touch this problem? And just think about what it means. Somebody just described, what does efficiency mean? Scott, get rid of those headphones for a second. Get rid of those.
Doing the most work that's the least work for them.
Okay, so it's a ratio of, it's just a ratio of how much work you're getting out compared to how much work you're putting in, right? That's one way to look at it. Okay, we're doing work on a machine, and if it's highly efficient, we're gonna get most or all of that work back, right? So that's one way we could say. It's gonna be, one definition is efficiency equals output work over input work, right? Okay, that's one good way to do it. Okay, what's another way then? What's another way of kind of getting to the same idea?
Like theoretical versus actual.
Yeah, right. So it's going to be, it's mechanical advantage. It's the actual mechanical advantage compared to what the theoretical mechanical advantage should be, right? In actuality, it's probably not as high as it theoretically it's predicted to be, right? So there we've got actual mechanical advantage over theoretical mechanical advantage. Okay, while we're on the subject of that, what is actual mechanical advantage?
Actually get out.
Okay, when you say actually, what does that mean?
Circumstantial. You had an experiment or something like that.
That'd be the theoretical would be what it ought to be, right? In theory, right? But in actuality, what is it that machines are doing for us? I mean, what is it that we always measure? What are they trying to do? Yeah, they're trying to multiply force, right? So in some cases, they may actually not be. They may actually be, we might be sacrificing force for speed. But we can always compare what the input force and the output forces are, right? Whether it's a big mechanical advantage or something less than one, right? So actual mechanical advantage is going to be it's going to be output force over input force, right? If it's multiplying the force by a lot, then we're going to get a much larger output force than input force. Okay, another way we say that sometimes, what do we say? We say resistance force over effort force, okay? What about theoretical mechanical advantage? What's that one? I mean, it's different from machine to machine, right? There's different ways of calculating for each simple machine, but in general, it's always something geometric, right? In one way or another, it's always going to be somehow, it's going to be input distance over output distance, right? Okay, and just think about that. You typically have to move, like if you're multiplying forces, you have to apply the force through a much larger distance, right? Then the output is actually moving the thing. If you're hoisting up a rock, you got to push the lever a long ways, and the crowbar is only picking the rock up a tiny bit, right? Okay, good. So now let's get back to business here. So back to the problem at hand. So if we've got a 100% efficient class 1 lever, and it's used to lift 691 newtons by applying a force of 236 newtons, the distance from the applied force to the fulcrum is 2.24. So the load is located how far from the fulcrum? So what are we really doing here then? How could we set this up as yeah, I mean, as some kind of an equation or ratio we can solve for the unknown? Because that's really what we want to be able to do here, right? So, alright, so what do we got?
Is there a specific amount, like, because if you just set them up to be equal to each other, they wouldn't necessarily lift it, would it? Like,
Well, okay, so,
you know what I mean? Like, it would just be in equilibrium.
well, okay, but equilibrium, now I know what you're saying, but let's think about that word equilibrium. Equilibrium refers to when all the forces on an object are balanced, right? See what I'm saying? So I know what you're saying, but it's not necessarily equilibrium that we're talking about. If it's 100% efficient, it just means that the input work and the output work are going to be equal, right? But the balance of force and distance is just going to change, right? Most of the time, we're going to trade big distance, small force for small distance, big force, right? Okay, so one way we could do this is by saying if it's 100% efficient, that means that the input work and the output work are equal, right? Does that make sense? So we could say, input work equals output work. And I guess that really comes from the 100% efficiency part would be that the ratio of output work over input work equals 1 as a decimal, 100%, as a percentage, right? And so then if we just multiply each side by input work, cross multiply, we get that, right? So what's the input work then?
236.
Okay, good, 236 newtons times 2.24. That's the distance from the applied force, right? That's the effort force to the fulcrum. And that must equal output force times the load is located, so we'll call that D sub R, I guess, or D output, whatever you want to call it, right? Does that make sense? And we're just solving for that.
Wait, so how do you know which length goes with which?
Based on the context, right? Because it's saying would you agree that that's definitely the input force?
Yeah.
Because that's the applied force. So the distance from the applied force to the fulcrum is 2.24 meters, right? So that defines the input distance, right? Okay, does that make sense? Okay, so that's how we'd set that one up, all right? What about,
Wouldn't that just, like, setting them equal to each other, wouldn't that just make it balanced to where it's not actually lifting it?
no, it is lifting it. It's lifting it, but look what the difference is gonna be. Look what the magnitudes of the two quantities are gonna be. Here you've got a relatively small force. I mean, it's roughly 1/3 as much force times that distance is gonna produce 3 times as much force, right? But what's the distance it's gonna move?
Right,
for?
yeah, I get that, but it just doesn't make sense to me, I guess, how that would be lifting it, not just setting it to where they're both balanced, like.
Oh, I see what you're saying. You mean, okay, I think I see what you're getting at. So I think what Kate's saying is to make the thing actually move, okay, so maybe you gotta give it a very slight bit of additional force to get it moving, and then once you get it moving, it'll move at constant speed. I got it, yeah, I see what you're saying. Right, so, I understand. Right, so, right, to get the thing, to pry it loose and get it moving, you might have to increase that like slightly above that, right? But then once it's moving at constant speed, there you go. Right, does that make sense? Okay.
Oh my gosh, really?
Okay, and really what's going on is, you can apply this much force, but we haven't really talked about, I mean, how heavy is the object that we're moving? Maybe the object that we're moving is a lot lighter than 691 newtons, right? You can apply that much force, which means you would be accelerating it pretty hard then, right? If you push down with that much, that's just telling you the amount of force you can deliver through that much distance. right? That may not be enough to move it, possibly. It may not move anywhere, right? But that's just mechanically, that's what the machine's gonna, that's what the output force is gonna be. Right, does that make sense?
Yeah.
Okay. All right. Next problem. I think probably a lot of these are gonna be pretty similar. So this is same kind of deal. We could probably skip that one.
Can
Right.
we do
Do that
one
one.
like, is this 10.2?
Yeah, we can go to a different one.
Can we go to 10.1, practice one?
Sure.
Go through that one real quick.
Yeah.
So it gives you the applied force of 235, and it gives you the whole length of the lever.
Right.
Would
Okay.
would
Yeah.
you just take that applied force and divide by the length of the lever?
Okay, so, all right, so before we move on, real quick on this one. This is kind of tricky, isn't it? I like this problem. So yeah, it's giving you the output force and the input force, right? Let's say that we're gonna call, it doesn't tell us either one directly. Let's just say that we call the input force X. What's the output force gonna be?
Why?
If the whole length of the lever is 4.25, and it's a first-class lever. If the whole thing is, right, if the whole thing is 4.25, and we're saying that that much of it is X, then how much is left over?
X.
Oh,
No.
no,
Y
like
minus X.
Well, okay,
Length
Total
minus
minus-
4.25 minus X,
Yeah.
right, exactly, right, if the whole thing, does that make sense? Okay, so if you're just gonna, because we don't know, we're gonna have to define a variable, let's just let X equal the input distance, then the output distance must be the whole lever minus the input distance, right? Okay, that's how you do that one. Then you'd end up with an equation involving X, right, which represents whatever you define it to be. And then if you solve for X, you get both of them. You get whatever, input distance, and then you can also find output distance by just saying that minus X, right? Okay.
We're like, yeah, sure.
I mean, well, let's just say, okay, so you get something, your equation might look something like this, right? So the force in, so work in equals work out, right? So that means input force, so 235 times X would equal.
608 times X minus Y.
Exactly, times 608 times 4.25
Yeah,
minus X,
yeah.
right? See what I'm saying? Where X equals, we have to define that X equals input distance. So effort distance or input distance, right?
How do you know which one's input and which one's output?
In this problem, well, you'd have to just say, I'm either gonna let X equal the input distance or the output distance, doesn't matter.
Well, but how do you know it's 608 times by the 4.25?
Okay, because, well, that's okay. The only reason I know that is because I define X to be the effort distance or the input distance. And so this is gonna be 608 times the output distance. If I had said X equals the output distance, then it would have been 608 times X equals 235 times
So you
4.25.
can do that too.
Sure, doesn't matter, just depends which one you're setting X equal to. Okay? All right, so,
Something wrong with the ends.
No, it's perfectly fine.
No, he got it wrong, but it said it was right.
What?
He's cheating.
show me
I think it's
afterwards.
just programming.
Right.
Uh-huh,
I'm not gonna
uh-huh.
argue.
Okay.
You know what? If Ian's gonna get it right on the test, he needs to be able to do it. Okay? I am just watching out for him. So you're welcome.
That's not what we're, oh, just kidding.
Okay, so this, well, I mean, while we're on this real quick, so something like this, if you're trying to find the actual mechanical advantage, then all you're doing, that's always just output force over input force, right? So you have to just, in the context of this problem, you just have to determine what's the output force and what's the input force. Okay, and it's not hard, but it's a little tricky. You gotta be very careful with it. And you gotta kinda ask yourself, when you wanna find output force, remember, output force is essentially, what did I do? So say I got it, what's the thing I have to accomplish? I have to move this thing that far. Well, the thing you have to move, whatever the weight of that thing is gonna be the output force, right? That's what you're getting done. The input force is when you're using the machine, how much force are you inputting to do the job, right? So, okay, so then,
So 301.1 would be the in,
was the input force, exactly, because that's the force that we're using on the ramp.
and then 33.7 times by gravity. would be-
Exactly, yeah, it's gonna be 33.7 times G, is gonna be the output force, good, okay? Input distance would be what?
305, 2.5.
Input distance,
4.53.
4.53, because that's the ramp once again, right? That's the distance up the ramp. And the output distance would be, if we didn't even have a ramp there, what job are we trying to do? We're trying to move that object up how far? 2.05, right? Okay. And then finally, same kind of thing, only now they're just asking for, there was some variability. It could have asked for theoretical mechanical advantage, or it might have asked for efficiency. I mean, if it was theoretical mechanical advantage, that'd be pretty easy, wouldn't it? That would just be that divided by that, wouldn't it? Right?
Something like
See what I'm saying? It's just gonna be output, input distance over output distance, right? Efficiency, what could I do? Well, I could either do the work stuff, like we did before, right, which is fine. I could say 31.5, let's see, I'm gonna do, efficiency is gonna be output work over input work, right? Yes,
that. On those things up there, is the first one actual mechanical advantage and the second one
Yes.
theoretical?
yeah. Our book just calls it mechanical advantage, but when you see MA, that's same thing as actual mechanical.
So what's IMA?
Ideal,
So that's theoretical.
theoretical ideal, same thing, yeah.
Uh,
Well, I think our book uses IDA.
AMA, TMA.
All right, so then we could say if we want to find output work, it's just going to be 31.5 times 9.8, right, times G, times 1.52 divided by input work is 120.1 times 7.61, right? Does that make sense? Okay.
Ian, don't say yes if you don't know.
Output, well,
It
this,
does make
output
sense.
work is output force, which is just mass times G, mg, right? Times output distance is how far did it move vertically, right? Input force is the force applied along the ramp. Input distance is the length of the ramp. Okay,
So those,
right?
divided by, okay.
Yeah, divided by, exactly. Okay, so now, let's see, Peyton, you wanted, let's go back here, you wanted, this one,
Yeah,
practice one,
yeah,
number
number 3.
3.
Wait, is it joules or something, or is it just nothing?
No, efficiency is just a number,
Oh,
it's unitless. Remember, because it really just means a percent.
That's not my.
yeah. So you.
That one?
Yeah,
Okay,
So.
so what about this then? This one is really just,
Oh, okay.
this is getting at the idea, let's think about, there's two parts to this. Worker carries a 17.7 kilogram box of nails, 4.8 meters vertically up a ladder. He's doing work, isn't he? Because he's applying a force equal to the weight of the tools, whatever he's carrying, nails, right? It's in the same direction as the force he's applying. He's moving vertically and he's applying the force vertically. Say it again?
Yeah, you times it by that.
The horizontal, exactly, but the horizontal doesn't matter. Once he gets up to the roof and he carries the box horizontally, he's pushing it in this, actually he's applying a force in this direction to support it. And he's walking in that direction, so displacement and force are at 90-degree angles, right? So there's no work being done. Okay, there's no force in the direction of motion, all the force is vertical instead, right? So all we'd have to do in this case, the only part that contributes is gonna be the weight, which is this, mass times G, right? Times 4.8, right? So this answer would be work
But you have to
equals,
times it by gravity?
yeah, 17.7 times 9.8 times 4.8, which is just force times distance. Make sense? But the horizontal part does nothing. Remember the example we did in class? We said, if I pick this object straight up 1 meter and set it on a shelf, that's the same amount of work as if I move it diagonally and put it on a shelf, right?
Is the diagonal 1 meter?
No, the diagonal is further, but let's say, well, I'm moving it diagonally to set it up on a 1 meter high shelf.
Can we do number 4?
Sure.
Oh, you're doing number 4? Oh, you don't have. I was like, what? Okay, and then
Okay, number 4, so what's number 4 saying? Okay, right, so this is the one with the kid throwing the ball up, right? I think we talked about, you might have gone there, we talked about this. You throw the ball up in the air, I think what's going on here, gravity is doing work, gravity's pushing down on the ball the whole time, right? So if I just throw the ball right up to the person on the balcony, how far does it move? Well, it's moving up 4.5 meters, right? And gravity is acting downward with 3.5 newtons of force. Okay, so then it's going to be negative work, right? Because the force is down, but the displacement is up, right? Well, what if the guy misses it when it's going up? It goes up in the air and comes back down and he catches it. Does that extra part change anything, right? Doesn't change a thing because the work gravity does, the negative work it does going up to the apex offsets the positive work it does pushing it back down to the guy, right? So really all you have to think about is just, you don't even have to worry about that 8.1 part. That's all that matters, right? And the reason that comes up is that gravity is a conservative force. It doesn't matter the path that you take to get from point A to point B, the work's going to be the same regardless, right? Okay. All right, all right.
So what's the difference between finding the efficiency and finding the mechanical?
There is a
Does
difference.
work and force?
Because the efficiency is different. You could have, the efficiency could be less than, it could be 50% efficient, but still have a large mechanical advantage, right? Mechanical advantage is actual mechanical advantage is how much is the force actually being multiplied. Theoretical mechanical advantage is how much do we predict in a perfect world the force should be multiplied with no friction or anything, right? And efficiency is just saying, what's the ratio of those two? How close is the actual to the theoretical? Or another way of saying it is, what's the ratio of the input or the output work over the input work? Either way, why wouldn't the output work be the same as the input work? Because there's been some frictional losses, right? So the actual mechanical advantage ends up being less than the theoretical by exactly the same amount.
I still don't understand.
On which one? On this one? Okay, so let me draw a picture with this one. So here's the ground, right? And here's the balcony. Okay. So if we throw this ball up in the air, right? When the ball's in the air, gravity is pushing down with the force of mg, right? Does that make sense? So to go from here to here, it's going to do a certain amount of negative work because it's slowing it down, right? If we let the ball go clear up to the top and then come back down, well, what's the difference? From there, let's color code this. From there up to there, the work done by gravity, let's just throw a number at it. Let's just say that going from 4.5 to 8.1, let's just say that it does negative 100 joules of work. Okay, how much work is it going to do from here to here, Pete, when it comes back down? Right, because the weight, the weight is 3.5 newtons, so that's the force gravity is down.
No, I should not understood.
The displacement is up. And so force times displacement is going to be work, but they're in opposite direction. So if you look at the formula that uses this one right here, right? That theta is actually 180, right? And the cosine of 180 is -1. So we just know, without even having to worry about the angles, we know if the work and displacement are opposite, then the work is negative. So when gravity, when it slows it down, so it comes to rest, it's
I'm guessing you don't work tonight.
the whole time it's doing negative work like that. And we know that.
This is your wiener. Look at his vacation.
then from there back down to the catch. Now gravity's pushing in the same direction. So if it does negative 100 joules going from the balcony to its highest point, from its highest point back to the balcony, it's doing positive work, right? And so really, this part does nothing to change the total work done by gravity. The only part that's gonna be important
My answer was.
is just gonna be the trip from the ground up to the balcony. Well, let's just say that that ended up being negative 81 joules type thing. And that's really all we have to count.
I wanna go like, mine says the boy throws a 4.3 Newton ball, 2 strike on the balcony, 5.4 meters directly up, has to try to take.
Yeah, just
So I can do that, but it depends on the gravity.
Well, that, no, gravity's already there. The way Ms. Pond, see, is given, you see what I'm saying? I see where the very effective, if that's in kilograms, then you're right, then we have to find the weight, because that's in kilograms. That's actually.
You're subject to the sign,
See
you
what I'm saying?
take notes, that's not, not saying that. Mr. Kell,
What are you guys, are you guys?
I mean, I just like draw a title and then stuff, and then title and stuff.
So, we might as well be taking it tomorrow, you know, when I was last time we took this weekend. There are some questions I know they understand. On request, which is, yeah, the text.
This one, no. Gotcha.
So I'm literally only being here.
What's that?
I'm only being here for like more than 5 minutes, so it's even worth being here.
Yeah, it is, it is.
Because if it's like nothing, then.
Yes, no, we're gonna review today.
God, review day here, testing